Our project, it focuses on the water atmospheric vapor entrapper or WAVE. So water scarcity is a huge issue, especially as climate change and increasing population causes more drought and increased demand for water. And so these are some of the statistics um, that we want to highlight, that 2 billion plus people live in countries where water supply is inadequate, and that 50% of the world's population could be living in areas facing water scarcity by 2025.
Sometimes it makes that not just talking about water. We started pouring water.
And we specifically were targeting the population in Western Cape, South Africa, which faces extreme water scarcity, with 19% of the rural population lacking access to a reliable water supply. And also in 2018, there was a situation called Day Zero where uh, the Western Cape almost ran out of water and they almost shut off like municipal water supplies and were considering starting to ration water out. And I think this highlights an important issue, which is that the water crisis is not just a health issue, it's also a socioeconomic issue, with it disproportionately affecting people living in rural areas and cannot afford to pay for their water.
All right, so it's just to piggyback off of what Marisol already said about the existing problem. So there are current companies, many companies actually targeting this issue. So many basically solutions exist within this claim, but a lot of it has like fundamental limitations. So for example, if you're looking at this plot, which is basically relative humidity with water output, for something like fog harvesting, where you literally put up giant meshes, I think someone posted this in Discord, you can capture a lot of water. However, the optimal around relative humidity is actually around 90 to 100, which is not feasible for many places. So there are some other options, such as using a desiccant wheel, which is this giant industrial wheel with desiccants embedded into it that basically spins, condenses, but this uses a lot of basically energy input, as well as these are very large scale commercial products. So what we have here is this is scaled to 1 kilogram of desiccant. For reference, what we have in front here, this is around 200 grams. So a lot of these wheels, they claim they can output like 100 liters of like 100,000 liters of water per day, but these are huge machines that basically take up entire room. So what we're kind of targeting is this region in the middle where there's not great technologies currently. And then this region, it might seem like, oh yeah, like why do we care? But more than 1.2 billion people actually live within this region, have water scarcity issues within this region. So that's what we were hoping to target, especially like given this graph of temperature versus also just relative humidity, we're targeting semi-arid regions. So what do we actually want? We basically want a highly portable design. As you see, we can just transport it really easily from the back of the room to here, a highly modularized design that is essentially biphasic. So, or bimodal in some sense. So we wanted to operate both within this kind of like arid kind of like seasons as well as during the humid seasons so that people have water year round. So part of it is we're going to rely on just like kind of like an um I guess like metal framework or iron mesh where you basically just fold it into the wave structure, hence the name wave. Um, so that could just be in the box during the relatively humid seasons where we don't actually need any additional input. Basically, you just put the mesh out there, it gathers water, you collect the water. However, during the drier seasons, we're going to implicate this like desiccants, basically that are then overlaid over it, such that you can basically take it off, put in as many as you need, depending on what condition or what kind of like relative humidity you're targeting. And the whole idea there is with the desiccant, it's kind of relying on this day-night cycle. So during night, we're basically opening this lid. This lid comes apart where you basically just absorb water. Put this in a place where you think you have the most airflow, where you have the most relative humidity. During the day, close it. Use evaporative cooling such that the water, I guess like that is captured by these desiccant beads, then condense onto this lid and then gets condensed out through this white tube or can also just be poured out from the bottom. So we have two basically collection methods, one where it's just passively pooling at the bottom, one where we're actually trying to actively condense it here. So to increase like the thermodynamic, like I guess like cycling and efficiency of this machine, there's also a fan here in the back. This is just a 3D printed fan that basically during night, it helps with the cooling. During the day, It basically allows for airflow such that we're not just like oversaturating the water pressure in here or water vapor in here, and nothing actually condenses in that sense. And everything here is just a solar panel, which is actually pretty cheap. So as a proof of concept, right? Like the main part of our thing basically relies on you have the grid and you also have the silicon beads. So we were trying to think, okay, so how do these beads work? So we set up this pretty simple experiment where I basically spiked in like certain amounts of water into this tissue paper, or it's just that paper in the back, put it in here, basically leave it there for a day, which is what our cycle is simulating. So what actually happens? So the beads that we're using specifically for our proof of concept are these color changing beads. When it's dry, it's kind of like this blue color right here. When it's like wet, it basically changes into pink. So that was basically after capture, and this is when we're trying to actually evaporatively heat it. So the main goal here is we basically use solar heating, right? Any sort of reflective surface put on top of it, make a really easy solar oven. If you have tinfoil, that works great. If you have a mirror at home, that also works great. And what we did here is basically just heated to roughly the temperature of a solar oven could achieve. And then what we see is, wow, we have condensation, and wow, the color changes back. So basically works out.
Condensation is fantastic.
Yeah,
There is water.
we were really surprised at how much we were actually able to get out of it.
It's actually quite a lot of water.
For sure. So basically this is a really basic graph, like as you're increasing in relative humidity, or I guess like in terms of the quite literal humidity conditions, the water that is gained as well as the water that we're able to recapture is around like 30% within this semi-arid zone. And for reference, the relative humidity here is, you go to the next slide, roughly around like this 20% to 30% range. So we're actually doing pretty well. We're a bit below the industrial desiccant wheel, but on the, I guess like the scale of the household, which is what we want our device to be for, it's actually like a decent amount. And then as you basically put in more desiccant, we're expecting water input or output to basically increase as well. And as Marisol mentioned before, we're not only trying to alleviate like the health issues, it's also kind of a socioeconomic gap in which I guess like individual households, especially in rural areas, don't have access to. They have to basically ask like these centralized agencies for water. And we're just saying, hey, can we maybe supplement that with a bit of like technology in your own household?
Okay, so moving on to our build versions. So our first version, we just had the desiccant layer flat, and we did this for like testing purposes, just to, well, first we created this like test environment where we put a humidifier in an enclosed box, and we kept our device in there for about 5 hours, and you can see the change from blue to pink. Let's see. This was like when it was pretty humid in there. And you can see like just some water pooling. And then this picture on the right shows the metal. You can see the droplets formed on the metal, which shows how pretty effective in harvesting those, the dew droplet things. Oh. Okay, so then next we took it to the hot room, and you can see that it pretty much dried up any water that was in there, and like, yeah, I guess evaporated it. And we took it outside. This was at night, and within 30 minutes, you could already see condensation forming on the slant of the glass as well as at the bottom where the wiring was. Yeah, it's kind of hard to see, but there's like water droplets like on the bottom that fell from the mesh. This is just another video kind of showing what the condensation looked like. So it happened pretty quickly after we took it out of the hot room, and just showed how effective like the passive cooling method is. And we tried to collect some of the water, but it was kind of a bit difficult with our setup.
Yeah, at that point we hadn't used the collection.
Yeah. And also just, I guess, to note was like usually this would be done over a span of like 24 hours with like the beads absorbing moisture during the day, and then at night the condensation occurring. But we were able to do like collect water within a span of 11 hours, obviously with some simulated environmental conditions. But Next was our second build version where we kind of updated a few things to really maximize like harvest efficiency. So we had the corrugated desiccant sheet, which increases surface area of the desiccant so we can maximize how much like air that the desiccants are able to come into contact with, which is also the solar powered fan. And then having a white collection tube and collection jug to increase like reflectivity and amount of time spent in passive condensation slash like cooling mode. And then also having a reflector that increases the heat directed onto the desiccants to improve like evaporation, which would lead to condensation. Oh wait. I don't know if I don't think we have time, but basically these are just videos showing that we got the motor running to get the fan working, and then also the solar panel, we hooked it up to a separate little fan and it was able to like get the fan running. So we weren't able to like finish that part, but some proof that that worked. And last, our next steps is just to evaluate like the optimal desiccant. There are a ton of different desiccant like formats, and we want the most efficient one. And then also changing the angle maybe to like improve collection of the condensation. Lastly, testing like efficacy with like all of our components combined, and also like adding a filter so that the water is actually like potable.
Because the evaporative cycle is a frequent cycle. So as long as the system doesn't grow mold and dissipate between it from time to time. Also, just the desiccant is a reusable material. So you get to tune and change. It's not as if anything is consumed. Technically, nothing is consumed in the system. So you can, your cost analysis can change based on if the unit operates for a year. You want to just increase the higher throughput, you could use more desiccant to change that around because there's no consumable technically. I was super awesome to see those droplets. That kind of was a little worried in terms of whether these desiccants are too efficient. Any questions? Yeah, I think one thing to do is this is a classic thermodynamic cycle. So you should really write this as the delta T between the total system, the delta humidity between the two systems, to be able to say as a, you run it as an engine, the energy taken in, what does the power output look like? So this would be a really beautiful